On a clear morning in 1998, workers on the Akashi Kaikyō Bridge in Japan noticed something. The deck was moving. Not violently, not catastrophically, but with a slow, purposeful sway, a gentle vertical undulation running the length of a span longer than any bridge on Earth. Nearly 2 kilometers of steel and cable, each main span stretching 1,991 meters between towers that stand 298 meters above the water, was breathing in the wind coming off the Seto Inland Sea. Engineers on site checked their instruments. The sensors confirmed what the eyes already suspected. The bridge was oscillating. And then, almost anticlimactically, everyone went back to work. Because the bridge was doing exactly what it was designed to do. That is the puzzle. A structure weighing roughly 181,000 tons, carrying 6 lanes of traffic across one of the most seismically active straits in the world, was swaying in the wind, and the engineers considered this a success. Here is what most people assume when they hear that bridges move in the wind: they assume the engineers are trying to stop it, that the goal is perfect rigidity, that a bridge trembling in a storm is a bridge failing. That assumption is completely wrong, and understanding why it is wrong requires going back to a catastrophe that changed the entire discipline of bridge engineering, and then following the physics all the way to the counterintuitive truth that movement, managed correctly, is survival. We begin on November 7, 1940, in Tacoma, Washington. The Tacoma Narrows Bridge was only 4 months old, a sleek, elegant suspension bridge with a main span of 853 meters. Its deck was unusually shallow and solid, a flat plate girder design that looked modern and clean. That morning, winds of roughly 64 kilometers per hour began rolling through the Narrows. What happened next was filmed, which is why it remains one of the most studied events in engineering history. The deck did not simply sway from side to side. It began to twist. One edge rose while the other fell. The oscillations grew larger with each cycle. Within an hour, the center span collapsed into the water below. For decades afterward, the popular explanation was resonance, the idea that the wind hit the bridge at its natural frequency, like a singer shattering a wine glass. That explanation stuck because it is tidy. It is also incomplete in a way that matters enormously. The actual mechanism was vortex shedding, and understanding it changes everything about how you read a modern suspension bridge. When wind flows over a flat, solid surface like the Tacoma deck, it cannot pass cleanly through. Instead, it separates at the edges and rolls into spinning eddies, vortices, that shed alternately from the top and the bottom of the structure. Each vortex, as it detaches, delivers a small push. Top, then bottom, then top again. This alternating push happens at a frequency determined by wind speed and the geometry of the deck. When that shedding frequency locked onto the natural twisting frequency of the Tacoma Narrows deck, which was roughly 0.2 Hz, one full twist every 5 seconds, the bridge stopped being a passive object in the wind and became an active participant. It began feeding energy back into its own oscillation. Engineers call this aeroelastic flutter. The wind was not simply pushing the bridge. The bridge's own motion was reorganizing the airflow around it, which then amplified the motion further. It was a feedback loop with no natural ceiling, and the bridge had no way to break it. The solid plate girder deck was the problem. It behaved like a sail, or more precisely, like a wing oriented exactly wrong for the conditions. Now here is the trick that every modern suspension bridge exploits, the one sentence you can repeat to a friend: the deck is not designed to resist the wind. It is designed to let the wind through. Look at a cross-section of the Akashi Kaikyō deck, or the Humber Bridge in England, or the Great Belt Bridge in Denmark. Instead of a solid plate, they use an open truss or a streamlined box girder with carefully shaped aerodynamic edges, often with vents and slots running along the center. The Akashi deck uses a stiffening truss system open enough that wind pressure passes through rather than accumulating. The Great Belt Bridge in Denmark, with a main span of 1,624 meters, uses a hollow steel box girder whose cross-section was tested in wind tunnels for years before construction began, a cross-section shaped to shed vortices symmetrically and at high frequency, so that the shedding rhythm never has time to synchronize with the bridge's own natural frequency. The deck effectively untunes itself from the wind. It hums, yes, it moves, yes, but it moves without locking into that fatal feedback loop. This is where the metaphor that makes it stick comes in. Imagine you are dragging your heel downhill to slow yourself on ice. If you dig in the heel hard and suddenly, you stop 1 foot but the rest of your body keeps moving, and you fall. But if you let the heel slide just slightly, maintaining contact and spreading the force over time, you descend in control. The aerodynamic deck does exactly that with wind energy. It never gives the wind a clean surface to grip, never allows energy to accumulate at a single frequency. It diffuses the force continuously rather than resisting it at a single point. But aerodynamic shaping alone is not always enough, particularly for very long spans where the natural frequencies are extremely low and the bridge responds to a wider band of wind conditions. This is where tuned mass dampers enter the picture, and where the engineering becomes almost philosophical in its elegance. A tuned mass damper is, at its core, a heavy object attached to the structure by springs and shock absorbers, calibrated to oscillate at exactly the frequency the engineers most want to suppress. When the bridge begins to sway at that frequency, the damper mass moves out of phase, it swings one way as the bridge swings the other, and in doing so it transfers momentum back into the structure in a direction that opposes the oscillation. The Akashi Kaikyō Bridge contains 20 tuned mass dampers housed inside each of its 2 main towers, pendulum-type dampers, each a substantial mass on a calibrated arm, tuned to the tower's natural sway frequency. The Millennium Bridge in London, which experienced an unexpected lateral resonance when pedestrians inadvertently synchronized their footsteps with the bridge's natural frequency on its opening day in 2000, was retrofitted with 37 fluid viscous dampers and 52 tuned mass dampers to resolve the problem entirely. The bridge now carries pedestrians without perceptible movement. Here is the engagement question worth sitting with for a moment. If you had to stand next to one of the machines covered on this channel when it is operating at full load, the Akashi Bridge in a typhoon, a running blast furnace, or a container ship entering a channel under its own momentum, which one keeps you up at night? Leave that answer below, because the reasoning tells you something real about where the engineering is truly remarkable. Back to the bridges. The false belief being corrected here runs deeper than most people realize. The common assumption is that the goal of structural engineering is stiffness, make it rigid enough and nothing bad can happen. The Tacoma Narrows was built partly with that logic. Its engineers used a shallow, solid deck because they believed the sheer weight and continuity of the structure would resist wind loads. What they built instead was a structure with a dangerously low torsional frequency and a geometry perfectly shaped to trap vortex energy. More rigidity, in that configuration, would not have saved it. A different geometry entirely was the answer, and that answer only came from understanding the aerodynamics. The Akashi Kaikyō spans a strait that sees typhoon-force winds and magnitude 8 earthquakes. Its design wind speed is 286 km per hour. The deck moves, the towers flex, the cables shift, by design. The entire structure is a calibrated dynamic system, not a static one. Engineers spent 10 years designing it, constructing 1:100 scale models and testing them in one of the world's largest wind tunnels. When the 1995 Great Hanshin earthquake struck while the bridge was under construction and shifted one of the towers by roughly 1 meter, engineers surveyed the damage and adjusted the design rather than starting over. The bridge absorbed the earthquake the way the finished structure is meant to absorb the wind, not by fighting it, but by participating in it intelligently. That is what the hum actually is. It is a conversation between physics and engineering. Every oscillation the bridge makes is a controlled response, shaped by aerodynamics, dampened by calibrated mass, tuned by decades of accumulated structural knowledge bought in part with the lessons of Tacoma Narrows. The bridge is not failing when it sways. It is succeeding. The engineers built it to move precisely because they understood that in a world of wind and earthquakes and thermal expansion, perfect stillness is not safety. It is brittleness. The next time you cross a long suspension bridge, notice the deck. Notice the open truss work or the tapered edge of the box girder. Notice the way the wind passes through rather than piling against it. You are looking at the answer to one of the 20th century's most expensive engineering lessons, built into steel and hung from cables at a height where the wind decides the rules. The engineers did not tame the wind. They learned its language. We are surrounded by impossible machines that somehow just work. Subscribe, one giant decoded at a time.